Metal identification lab. So in this lab, we're going to be determining the types of metals in the samples we've acquired based on physical properties. So the physical properties we're going to measure are things like hardness, volume, density, and magnetism. So I'll just give you a quick rundown of how we're going to do this on all of them. Some for hardness, we're going to use the Rockwell hardness testers you can see over here. Or we will use a magnet to just touch it to the metal to see if it's magnetic, and to find its volume and through that calculate density. We'll use Archimedes' principle, in which basically the theory behind it is when you put an object into a bowl of water, the amount of water displaced is equivalent to the volume of the object that you placed in the water. So that's the theory behind the lab. Let's get started.
Lab, and I'm going to perform some tests for these two samples. First, I'm going to measure its mass, and I'm going to use the digital scale, and I will reset it. There you go. And now I'm just going to place the sample on the scale, and it reads 98.1 grams. I'm going to take it back and place the second sample on the scale, and it reads 116.7 grams. And now I'm going to check the samples for ferromagnetism, and I'm going to use a simple magnet. I'm going to attach it to the sample, and as you can see, it does not stick, which means it's not ferromagnetic. Now the second sample is ferromagnetic, that's why it sticks. There you go. And that'll be it.
Another one of the aspects of the metal identification lab, and this is using the overflow can and Archimedes' principle to determine the volume of the various samples. So in order to set the can at 0, you have to pour excess water into the overflow can until you see the overflow start. Then you wait until the overflow ceases. This may take a few seconds, and when you see it stop, that means it's ready to drop your sample. So we'll start with the rolled steel sample. Remember to pop your beaker under where the overflow would come, so you can measure the water that's displaced. And you proceed to drop the sample at roughly the middle of the can, so that it doesn't touch the walls or the floor. And then we wait for the overflow to stop. Remove the sample. And then we use the amount that is displaced to find the volume. This one appears to have displaced 14 milliliters, which would be equivalent to 14 centimeters cubed. And then we do the same thing for the aluminum sample. So we set the overflow can. Dump the beaker. Once it ceased, we're ready. We're now doing the aluminum sample. Prepare the beaker at the overflow. Drop the sample to the middle. Don't allow it to touch the walls. Once again, when the overflow stops, it means you're ready to remove your sample. And ready to read your reading. For the aluminum, I've got 44 milliliters displaced, which means that its volume is roughly 44 centimeters cubed. And that's pretty much this aspect of the metal identification.
One of the elements we need to measure is the volume of each each sample. To do that, we are going to use this caliper to measure the height, length, and width of each sample, of the square ones, and then the height and the diameter of the cylindrical ones. So, start with this one. As you can see, we get a diameter of about 1 inch. The height of about roughly 1 inch. With that, we can calculate the volume, and along with the mass, we can calculate density. Oh. So we got 2.6 for the height. Got roughly 1 for the width. And again, 1 for the height.
Now for the metal identification lab, we're going to be testing the hardness of these two materials. We've made a scientific guess that this material is most likely hot-rolled steel, based just on its texture and appearance. So we're going to test it on the C-scale. So first, look at the surface and find a smooth portion that does not already have a previous indentation on it, and align it with the bottom of the indenting. Next, we have to fasten it until the indenter makes contact with the surface of the material, like so. Now that it's touching, we have to continue to tighten it and raise the platform until this small pointer is pointing towards the little dot, telling us that it's on. Perfect. Now all we have to do is use this knob to set the scale to 0. And now that it's 0, we can simply release the load, like so. Now all we do is wait until the load is fully applied and the needle stops turning. And it looks pretty close. So now we release the load and read from the scale. So the hardness that the tester has measured for this sample is 66 on the Rockwell hardness C-scale. So now that that's done, release the sample, and we can move on to test this sample, which we are assuming is aluminum, on the Rockwell hardness B scale. So let's go do that. Now, following the same procedure as before, we find a smooth portion on the surface that has not been previously tested, and align it with the bottom of the indent. Now, turn in, raising the platform so that the material is touching the indented. We continue to turn until the small knob is aligned with the black dot. Now that we have alignment, we simply have to rotate the scale until it is 0. So right there you can see the needle is aligned with the 0 on the scale. So now we can release the load, and just like before, we wait until the needle has stopped turning on the scale, meaning that the load is fully applied. It looks to be about good, so we can release the load and read our value. It seems we got a value of about 56 on the Rockwell hardness B scale. So that's the reading for this metal.
We have taken all the measurements, we calculated density based on those measurements. We then made assumptions for each sample based on the test we performed, and density values calculated. For analysis data, please refer to our paper copy report. For the errors involved in these tests, we found out that submerging samples into water to determine their volume was not an effective way to measure. There was not an effective way of measurement. due to multiple tests for the same sample, giving us different results. Also, the submerging tests weren't accurate for the small samples. Volume errors could significantly decrease the accuracy for density calculations and obscure our predictions to identify the sample.